Section: Introduction. In this section, we will discuss the introduction of large language models, LLMs, and their widespread use in various fields such as medicine, education, and software development. Despite their success, LLMs often produce nonsensical or inaccurate responses, known as hallucinations, which can be risky in critical applications. Detecting these hallucinations is crucial, and one way to enhance LLM reliability is by estimating the uncertainty of their outputs. Predictive uncertainty in LLMs can indicate errors or hallucinations, especially in tasks like multiple-choice question answering. By measuring uncertainty, we can avoid incorrect predictions and seek advice from human experts when needed. However, accurately estimating uncertainty in free-form natural language generation is still a challenging research area. The complexity of language and LLMs makes it difficult to apply traditional uncertainty quantification methods. Language outputs can have different types of uncertainty, including lexical, syntactic, and semantic uncertainties. Semantic uncertainty, which relates to the accuracy of the generated response's meaning, is particularly important. Existing methods like semantic entropy, SE, estimate uncertainty based on semantic equivalence but lack a metric to capture nuanced semantic similarities between responses. To address this limitation, we introduce Kernel Language Entropy, KLE, which incorporates a semantic distance metric into uncertainty estimation. KLE utilizes semantic similarities among generated responses by measuring the von Neumann entropy of positive semi-definite kernels that encode the distance in the semantic space. This approach allows us to consider the relationships between generated responses or semantic clusters when estimating uncertainty, making KLE more effective at capturing the semantics of generated texts compared to previous methods. We demonstrate that KLE is more expressive than SE in distinguishing uncertainty in certain cases. Importantly, our method does not rely on token likelihood and is applicable to both transparent and opaque LLMs. Our contributions include proposing KLE as a novel uncertainty quantification method, suggesting effective design choices like graph kernels and weight functions, proving the generalization of KLE from semantic entropy, and achieving state-of-the-art results through empirical comparisons across various tasks and LLMs. Section Summary. In this section, we introduce the challenges posed by hallucinations in large language models, LLMs, and the need for reliable methods to detect them, especially in high-stakes applications. To address this, we propose Kernel Language Entropy, KLE, as a novel method for estimating uncertainty in natural language generation by incorporating semantic similarities using a distance measure in the space of generated answers. KLE outperforms semantic entropy by capturing more nuanced semantic relations between generated texts, making it a valuable tool for improving uncertainty quantification in LLMs across various tasks and model sizes. Section: Kernel Language Entropy. In this section, we introduce Kernel Language Entropy, KLE, our new method for calculating semantic uncertainty by considering detailed similarities between generated texts to improve uncertainty estimation. We present two versions of KLE. The first one, called KLE, works directly on the generated texts, while the second one, KLEC, operates on semantic clusters. To illustrate the benefits of KLE, especially the KLEC variant, we use a scenario where two language models, LLMs, are queried. LLM_1 produces outputs that are all semantically different, while LLM_2 outputs are semantically similar but not identical. If we assume an equal number of clusters in both LLMs and equal probabilities for these clusters, traditional methods like SE would wrongly predict equal uncertainty for both cases. However, KLE correctly assigns lower uncertainty to LLM_2 outputs because its kernels consider the semantic similarities in the outputs. Before diving into KLE, let's revisit the concept of a positive semi-definite, PSD, kernel. A PSD kernel is a symmetric function that satisfies certain mathematical properties. We then define semantic kernels, denoted as K_sem, as positive semi-definite kernels that capture the semantic similarity between generated texts. These kernels should reflect that texts are more semantically related if the kernel value is higher for them. Similarly, we define semantic kernels for semantic clusters to capture similarities between clusters of texts. Instead of defining semantic kernels directly for individual model outputs, we can also apply KLE to clusters of texts with semantic equivalence. This variation is called KLEC. While KLE is more general for complex clusterings, KLEC is more practical and easier to interpret due to its smaller kernel sizes. The computational complexity of KLE is similar to SE, involving multiple sampling steps and entailment model runs. Additionally, KLE requires elementary operations for kernel and VNE calculation. The cost of these operations is minimal compared to the overall computation through the models. We also discuss constructing semantic kernels over LLM outputs or semantic clusters using NLI models and graph kernel theory. KLE allows flexibility in combining kernels from different methods, such as multiple NLI models or graph kernels, using convex combinations. Furthermore, we show that the semantic kernels in KLE provide more information than those in SE. We demonstrate that KLE can recover SE for any semantic clustering, and the detailed proofs are provided in the appendix. Section Summary. In this section, we introduce Kernel Language Entropy, KLE, a novel method for quantifying semantic uncertainty by considering fine-grained similarities between generated texts. We present two versions of KLE, one that operates directly on generated texts and another that works on semantic clusters. KLEC, a variant of KLE, focuses on semantic equivalence clusters, offering a more cost-effective and interpretable approach compared to the general KLE method. Section: Related work. In this section, we have explored various works related to uncertainty quantification in machine learning. The von Neumann entropy, VNE, has been extensively studied in machine learning, particularly in the context of generative adversarial networks, GANs, and sample diversity analysis. Techniques for estimating language entropy have a long history, dating back to the 1950s, and are now widely used in natural language processing for tasks like calibration in classification and improving model performance in sentiment analysis and named entity recognition. Calibration techniques have also been beneficial in machine translation tasks. Challenges in estimating uncertainty in sequential models have been discussed, with previous works using language models, LLMs, to understand uncertainty through various methods like fine-tuning and generation querying. Uncertainty quantification has been applied to long text generation and Bayesian modeling of LLMs to enhance calibration in multiple-choice settings. Our experiments cover a wide range of datasets and models across different natural language generation tasks. We use various LLMs and a specific NLI model for semantic graph or cluster definitions. To evaluate our method, kernelized language embeddings, KLE, we compare it with several baseline methods such as semantic entropy and token predictive entropy. We propose two semantic kernels, K_heat and K_full, for KLE, derived from a weighted graph based on NLI predictions. These kernels are evaluated using metrics like AUROC and AUARC to assess their ability to predict model responses and improve model accuracy by rejecting uncertain answers. Sampling methods are employed to evaluate model accuracy, and statistical significance is determined through experimental scenarios and confidence intervals. Our results demonstrate that KLE outperforms existing methods across various scenarios and models. The heat kernel variant of KLE consistently achieves superior results compared to baselines, even in black box scenarios. Hyperparameters for KLE can be chosen effectively without validation sets, as default settings yield comparable results to validated choices. Comparing different design choices for KLE, we find that the heat kernel over a weighted semantic graph is the most effective. KLE excels in capturing fine-grained semantic relations, outperforming methods like semantic entropy in complex language generation tasks. This is illustrated through an example from the NQ Open dataset, showcasing KLE's ability to provide better uncertainty estimates. Section Summary. In this section, we explore the related work in machine learning, focusing on the estimation of entropy in language and uncertainty quantification techniques widely used in natural language processing tasks. Various methods have been proposed to estimate uncertainty in sequential models and improve model performance, including calibration techniques and diverse sampling strategies. Our proposed method, Kernelized Language Embeddings, KLE, outperforms previous approaches by estimating more fine-grained semantic uncertainty, enhancing model accuracy, and providing better uncertainty estimates in complex language generation scenarios. Section Discussion. In this section, we tackle the challenge of measuring semantic uncertainty in LLMs, which is crucial. We propose a method called KLE that uses semantic kernels to navigate the semantic space of answers, allowing for a detailed estimation of uncertainty. KLE is a more advanced version of semantic entropy. By creating NLI-based semantic graphs and kernels, and examining kernel hyperparameters, we offer specific design choices. Through evaluations in various natural language generation domains, KLE has shown better performance than existing methods. Our approach is versatile, working well in both white and black box scenarios, making it applicable in many practical situations. We aim to encourage further research that focuses on semantic similarity rather than equivalence to estimate semantic uncertainty in LLMs. Our work contributes to the advancement of safer and more dependable use of LLMs. KLE can enhance applications involving LLMs by providing more precise uncertainty estimates, which can help filter out incorrect outputs. One drawback of our method is that it requires multiple samples from an LLM, which can increase the generation cost. However, in critical safety tasks, ensuring reliability in uncertainty estimation through KLE is crucial, outweighing the cost of generating multiple answers. While we concentrate on semantic kernels from NLI-based semantic graphs, exploring other semantic kernels like embeddings is also important. Lastly, given the diverse nature of NLG applications, it is essential to carefully assess the method for other potential uses of LLMs, such as code generation.